All right, greetings and salutations, everybody. Welcome to the Ninja podcast for kinetic energy. We'll also be talking about the conservation of energy, probably not till the next podcast, but we're going to introduce it here. So we've already talked about work. Remember that work equals force times distance, or force times distance times the cosine of whatever angle we're given, because we're only worried about stuff that's traveling in the x direction. So cosine will give us that component in the x direction. And I mentioned that the units of work are joules, just like Mr. Adam Joule. The units for energy, the units for work, are the joules, because Mr. Joule has tons of energy. So now let's look at one of the forms that this energy can take. We're going to talk about kinetic energy first in this podcast. Kinetic, or kinematic, equals motion. So remember we did the kinematics equations. Those are all equations for motion. So when you're thinking kinematic equations, we think the laws of motion. So kinetic energy has to deal with the motion, or the energy of motion. So I'm going to show you how we derive the formula for kinetic energy. So first, we start with our work equals force times distance, and we know that force equals mass times acceleration from Newton's second law. So we have work equals force times distance, so W equals, that's a crappy color, choose a different one. W equals F times D. Now we're going to substitute Newton's second law in for the force. So work equals mass times acceleration times D. Yes, work makes me very mad too. So if we use this kinematics equation, remember this, Vf squared equals Vi squared plus 2A D, which also stands for your delta x, means the same thing. Change in x, this D and that delta x, same thing. So we're going to solve this equation right here for AD. So when we solve this for AD, we get Vf squared minus Vi squared all over 2. So now we know what AD is. We can substitute it into here. So now work equals mass times Vf squared minus Vi squared all over 2. And to make it look a little nicer, which is the way you're going to see it most of the time, so work here is going to equal your kinetic energy. It's actually a change in kinetic energy because we're going to have two different quantities here. So carrying out all this stuff, putting it all together, we get 1/2 mass times the final velocity squared minus 1/2 times mass times the initial velocity squared. So kinetic energy is just, if I just want to know the kinetic energy of one object at a certain point, it's 1/2 its mass times its current velocity squared. If I'm talking about work, I want to know the change in kinetic energy, so I then had to take into account the final velocity and its initial velocity. So we're just going to do a simple problem, just asking for kinetic energy. You don't have to worry about the change or the work right now. So example number 1, what is the kinetic energy of a train car with a mass of 67,132 kilograms traveling at 30 kilometers per hour? So we don't like kilometers per hour. We like MKS units. So we have to convert that into something first before we do anything. So we have 30 kilometers over 1 hour. We're going to have to convert this into meters per second. So in 1 kilometer, 1,000 meters. So that gets rid of our kms. Now we got to get rid of our hours. And in 1 hour, there are 3,600 seconds. And that gives us a total of 8.333 meters per second. Now it's a simple problem. Kinetic energy equals 1/2 mass times velocity squared. 1/2 times your mass, which is huge, times velocity. So we get a grand total of 2,330,000 joules. So we get kilograms times meters squared over seconds squared. That's a joule. Usually when things are this huge, we use kilojoules instead. So in kilojoules, there are 1,000 joules in every kilojoule, so this becomes 2,330 kilojoules. More common to see the kilojoules when we're talking about a lot of energy. Pretty easy, 1/2 mv squared. So trains, they take a long time to come to a stop. So the train car from the previous problem starts braking 1 kilometer before a train station. What is the force that the brakes must apply to stop the train in time? So the energy of the train car from before was the 2,330 kgs. So the brakes need to do negative work on the train car to remove this kinetic energy. So we know the final kinetic energy is going to be 0 because it comes to a stop. So because the v is going to be 0, 1/2 times mass times velocity is going to be 0. So we use something called the work energy theorem. So the initial energy plus the work equals the final energy. So we know here that the initial energy we got from the last problem was 2,300 kilojoules. Oops, 2,300 kilojoules, not kilograms. 2,300 kilojoules plus whatever work we get equals the final energy, which we said was 0 because the train car comes to a stop. So therefore we see that work equals negative 2,300 kilojoules. But we're looking for force, so we have to do something else. Remember, work equals force times distance. So to get that force by itself, we have to do the force equals our work divided by our distance, which is 1,000 meters, 1 kilometer. Yeah, that's 1 kilometer. We don't like kilometers, we like meters. So you get a total of 2,330 newtons. Now, I know 2,300 divided by 1,000 gives you 2.3, but remember this is kilojoules. So basically this 1,000 meters here just knocks off that K, and it just becomes newtons. And there's just me going over it. All right, apparently I forgot to hide that. So that force, that 2,330 newtons, that's roughly the force of 3 people standing on top of you. You know how bad that would probably feel. Do not try that at home. So you can kind of figure that out real quick. So 3 people times their mass times gravity, which is their force of gravity, which is their weight. Say average person's about 70 kilograms, about 150-ish pounds. So 3 times 70 times 9.8, it's roughly 2,058 newtons. That's pretty close to the amount of force needed to stop that train. It's 3 people standing on top of you. Oh, where's that? So therefore, trains are very hard to stop. That's why you shouldn't try to race trains and cross the tracks in front of them, because they really can't stop too quick. So side note, is this energy lost? So where does all this energy go? That 2,330 million kilojoules of energy, like where does that go? Does it just go into the atmosphere? Does it just disappear? No, it doesn't. That energy is actually converted into other forms because energy is conserved. We'll talk more about conservation of energy in the next podcast, but that energy is never lost. Just like matter can neither be created nor destroyed, energy cannot be created nor destroyed. So one more problem. A car, about 750 kilograms on flat ground, increases its velocity from 20 meters per second to 30 meters per second. What was the work done by the engine? So if you remember, the work equals the change in energy, and this time we're talking about kinetic energy. So now you have to use the whole equation, the final velocity squared and the initial velocity squared. So since both of these share a 1/2 and an m, pull that out front, make it a little easier to work with. Vf squared minus Vi squared. Now it just becomes simple plug and chug. 1/2 times 750 kgs times your 30 meters per second, that whole thing squared, minus your 20 meters per second, that whole thing squared, and you get a work of, crap, where's my answer to that? Hopefully I just pull out my handy dandy little calculator. Ah, no, there it is. So you get a work of 187.5 kilojoules. And here's a little conceptual question for you. So we're going to compare the energy required to accelerate a car from 0 to 10 miles per hour and from 20 to 30 miles per hour. Which case do you think is going to be bigger? You think it's going to be, they're going to be equal to each other? You think this guy is going to be bigger than this guy, or this guy is going to be bigger than this guy? Or do you think we can't solve it? Or, you know, Z, you just don't give a crap. So think about it real quick. You're changing, your speed's still changing by 10 miles per hour in both cases. So is it going to matter? So we can conceptually think about this real quick. So in case one, your change in kinetic energy be 1/2 times your mass times your final velocity squared minus your initial velocity squared. So 1/2 the mass is going to be the same for both problems. So what we're really looking at is just the final velocity squared minus the initial velocity squared. So the final velocity is 10 squared. Initial velocity is 0. So that's a change of 100. Now if we're doing it over here, same thing, final velocity squared minus your initial velocity squared. I know you can't do that because these are miles per hour and you should convert these to meters per second first, but it's just conceptual. It's going to still work out roughly the same way, just going to have slightly different numbers, but the proportions are going to be the same. So now we have 30 squared minus 20 squared. That's 900 minus 400. So that's a difference of 500. So you can see it's going to require more energy to accelerate a car from 20 to 30 than it does from 0 to 10, even though it's only changing by 10 in both cases. That's because these guys are squared. If these squares weren't there, it'd be the same. But they're there, so we have to deal with them. So it's going to be more energy after you're already moving to accelerate. And that does the end. Stay tuned for potential energy.